A dark world drifts alone through the endless void between stars. These are rogue planets, cosmic orphans untethered from any sun, and they are some of the most enigmatic objects in the entire universe. By the end of this journey, you will discover 30 incredible facts that completely redefine what a planet can be. We will uncover how these solitary worlds are born, investigate their potential to harbor alien life in total darkness, and reveal the staggering truth about their numbers. What do you think it would be like to stand on a world with no sunrise, forever adrift in the silent, starless night? A rogue planet is defined by its solitary journey, a world of planetary mass traveling through the dark of interstellar space, completely free from the gravitational embrace of any star. Unlike the 8 planets in our own solar system, which are eternally bound to our sun, these wanderers answer to no central sun. Their path is not a predictable, repeating ellipse around a star, but a solitary trajectory through the vast galaxy. This fundamental difference separates them from every other type of planetary body, even dwarf planets like Pluto, which still orbits the sun, or large asteroids that are typically part of a system. They are the ultimate independent travelers of the cosmos, completely untethered and moving on their own accord through the void. These solitary journeys begin with a cosmic act of violence. The most widely accepted origin story for rogue planets is one of chaotic beginnings and gravitational betrayal. Picture a young solar system, a swirling disk of gas and dust coalescing around a newborn star. Within this disk, multiple planets are forming, their orbits still unstable. As these young, massive worlds jostle for position, their immense gravitational fields interact in a dangerous dance. A close encounter between 2 giants can act like a gravitational slingshot, where one planet violently flings the other out of the system entirely. It is a celestial eviction, an event of unimaginable force that sends a world careening into the interstellar darkness, its path around a star severed forever. This dramatic ejection is not some rare cosmic fluke. Current theories suggest it is a surprisingly common part of planetary system formation, a standard outcome of the gravitational turmoil that shapes young families of planets. In the grand construction of a solar system, it seems some worlds are simply thrown from the nest. But ejection is not the only path into darkness. Another, more solitary origin story exists for these wanderers. Some rogue planets may never have known a sun at all. They could be true cosmic orphans, born not from the debris around a star, but directly from the collapse of small, isolated clouds of gas and dust in deep space. This process mirrors how stars themselves are formed, just on a much smaller, darker scale. Imagine a lonely pocket of interstellar material, too small to ignite into a star, slowly coalescing under its own gravity into a solitary world. This planet would begin its existence in total isolation, a free-floating object from its very first moment. This idea fundamentally challenges what we even mean by the word planet. Our traditional definition requires a world to orbit a star. But what do you call a planet mass object that formed exactly like a star, alone in the void? This question blurs the line between planets and a class of objects known as brown dwarfs. Brown dwarfs are often called failed stars. They are balls of gas that formed like stars but lack the mass to sustain nuclear fusion in their cores. The smallest brown dwarfs can be similar in size to giant planets, creating a puzzling gray area in our cosmic classifications. Is a Jupiter-sized object that formed alone from a collapsing cloud a very small brown dwarf or a very large rogue planet? The distinction comes down to its formation history, something incredibly difficult to determine from light years away. This mystery fuels an ongoing and vibrant scientific debate. Astronomers are actively investigating which birth story is more common. Are most rogue planets rebellious teenagers kicked out of their stellar homes, or are they lonely only children, born and raised in the deep dark? the answer could reshape our understanding of planetary formation itself, suggesting that the galaxy might be filled with two distinct populations of wanderers, one born in chaos and the other in profound solitude. The profound isolation of these worlds translates into an environment of almost unimaginable extremity. A typical rogue planet exists in a state of perpetual and absolute darkness, a night without end. There is no star on the horizon, no dawn to break the blackness. This unending darkness is matched only by the cold. Without a sun to bathe them in warmth, their surface temperatures plummet to just a few degrees above absolute zero, the theoretical point where all molecular motion stops. To put that in perspective, the surface of Pluto, in the distant reaches of our own solar system, is positively balmy compared to a rogue planet. The coldest temperatures ever recorded in Antarctica do not even come close. This is a deep, penetrating cold that would freeze the very air we breathe into solid blocks, a chill so profound it defies earthly comparison. Where could any warmth possibly come from in such a frozen wasteland? The answer lies deep within the planet itself. The primary source of heat is not external but internal, generated by the slow, steady decay of radioactive elements in its core, much like the geothermal energy that heats Earth's interior. A young rogue planet, freshly ejected from its system, might also retain some residual heat from its violent birth, a fading memory of the cosmic forge that created it. But this internal warmth is a faint whisper against the overwhelming cold of space. It might create a slightly warmer layer deep beneath a world-frozen crust, but at the surface, the reign of cold is absolute and eternal. This raises a haunting question: could life, in any form we can comprehend, find a way to exist in such utter darkness and cold, sustained only by the faint, dying embers of a planet's own heart? Yet within this seemingly sterile deep freeze lies one of the most exciting possibilities in all of astronomy. Some rogue planets could be hiding vast, liquid water oceans beneath their frozen surfaces. These would not be surface oceans like those on Earth, but secret seas locked away under miles of solid ice, kept warm by the planet's own internal heart. The primary source of this heat is radiogenic heating, the steady, relentless decay of radioactive elements like uranium and thorium deep within the planet's core. This natural process acts like a built-in nuclear reactor, generating enough warmth to melt ice from below and sustain a global ocean in perpetual darkness. It is a world with a frozen crust shielding a warm, watery heart, a planet that is an ice shell over a hidden sea. There is another potential heat source, one familiar from our own solar system. If a rogue planet has a large moon, the gravitational tug of war between them can generate immense tidal forces. This constant flexing and friction, known as tidal heating, can pump enormous energy into the planet's interior, supplementing its internal warmth. This is the same process that keeps the subsurface ocean of Jupiter's moon, Europa, from freezing solid. This concept fundamentally revolutionizes the search for alien life. For decades, we have focused on the habitable zone, that narrow orbital band around a star where liquid water can exist on a planet's surface. Rogue planets shatter that paradigm. Life on such a world would not rely on the light of a distant sun, but on chemical energy and geothermal heat, thriving in an eternal, sunless abyss. We already have proof of concept right here in our cosmic backyard. Moons like Europa and Enceladus are not planets, and they orbit stars, but they demonstrate the principle perfectly. They are frozen worlds with internal oceans, and scientists consider them among the most promising places to find life beyond Earth. A rogue planet is essentially a scaled-up version of Europa, but one that is completely free-floating and independent. The potential habitats within these dark oceans could be vast, stable for billions of years, and completely isolated from the surface universe. Imagine a world where the only light comes from deep-sea volcanic vents, and entire ecosystems could evolve in total isolation, unaware of the concept of a sky or a star. This transforms the lonely rogue planet from a frozen wasteland into a potential ark, a sealed biosphere voyaging through the galaxy with its secrets held deep within. Finding these dark wanderers presented an immense challenge for astronomers. How do you see a world that emits almost no light of its own, drifting in the vast emptiness between the stars? The breakthrough came not by looking for visible light, but by sensing the faint, telltale warmth of their formation. In the early 2000s, powerful new telescopes and sensitive infrared detectors turned their gaze toward dense, dark clouds of gas and dust, the very nurseries where stars and planets are born. It was within these cosmic cradles that the first rogue planet candidates were spotted. Objects with names like OTS-44 and CHA 110913-773444 were not orbiting any visible star. They were isolated, planet-sized bodies, and they were still glowing with the residual heat from their relatively recent birth. This infantile warmth made them detectable in the infrared part of the spectrum, where their dim glow could be distinguished from the absolute cold of the surrounding space. Confirming their nature was a meticulous process. Astronomers had to rule out the possibility they were simply distant stars or brown dwarfs by carefully measuring their mass and temperature. These objects fell squarely into the planetary mass range, too small to be failed stars. This was the moment a theoretical possibility became an observational reality. The discovery of these lonely worlds opened an entirely new window into the cosmos. It proved that planets could indeed exist on their own, untethered from stellar parents, and it launched a whole new, exciting branch of astronomy dedicated to finding and understanding these dark, nomadic worlds. This method of detection relies on one of the most profound concepts in physics, gravity's ability to warp the very fabric of space and time. When a rogue planet drifts perfectly in front of a distant, unrelated star, its gravitational field acts as a natural lens. It subtly bends and focuses the light from that faraway star, causing a temporary and precise brightening. From our vantage point, the background star appears to flare up for a short period, perhaps just a few hours or days before fading back to its normal brightness. This event is not a steady glow but a distinct, predictable spike in light, a signature written in gravity itself. The entire process is incredibly delicate. It requires a near-perfect alignment between us, the rogue planet, and the distant background star. The planet itself remains completely invisible, a dark silhouette whose presence is revealed only by the way it manipulates the light of another object millions of light years away. This technique, known as gravitational microlensing, is our most powerful tool for finding these cosmic ghosts. It allows us to detect worlds that are otherwise completely undetectable, planets that emit no light and reflect no starlight. Because microlensing events are so brief and depend on random alignments, they provide a kind of cosmic census. By monitoring millions of stars continuously and counting these rare brightening events, astronomers can create a statistical estimate of just how many rogue planets are drifting through the galactic darkness. The numbers this method suggests are nothing short of staggering, pointing to a galaxy filled with far more unseen nomads than stars we can see. The scale of this hidden population is almost beyond comprehension. Microlensing surveys have revealed a staggering truth. There may be more rogue planets drifting through the dark of our galaxy than there are stars. Let that sink in for a moment. The Milky Way is home to an estimated 100 to 400 billion stars. Each one of those stars could have its own family of planets, yet the current data suggests the number of solitary rogue worlds is even greater. We are talking about billions, perhaps even trillions of these free-floating worlds. This means the most common type of planet in the entire universe might not be an Earth or a Jupiter orbiting a sun. It could very well be a dark, sunless wanderer, a planet that answers to no star. This statistical conclusion turns our understanding of the cosmos inside out. We have spent centuries looking up at the stars, assuming that is where the planets are. But the silent, empty spaces between those points of light are not empty at all. They are teeming with unseen worlds, a vast, dark archipelago of planets on eternal solar journeys. This invisible majority represents a fundamental part of the galactic architecture, a hidden dimension of planetary existence we are only just beginning to appreciate. Could one of these cosmic drifters be a secret resident of our own solar system? The outer darkness beyond Neptune is not entirely empty. We see its influence not in reflected light, but in the strange, clustered orbits of small, icy bodies in the distant Kuiper belt. Something massive seems to be herding them, its gravity sculpting their paths. This hypothetical object is known as Planet 9. While it could be a giant world that formed in our solar system's early days and was flung outward, another compelling theory exists. Planet 9 might not be a native at all. It could be a rogue planet, an interstellar orphan that was captured by the Sun's gravity long ago. This would explain why we have not found it yet, and why its proposed orbit is so distant and tilted compared to the rest of the planets. It would be a permanent visitor that settled in the farthest suburbs of our stellar neighborhood. We have already witnessed smaller interstellar tourists. The strange, cigar-shaped object named Oumuamua and the comet Borisov were both confirmed to be visitors from other star systems, passing through on their endless journeys. If small asteroids and comets can traverse the galaxy, then entire planets certainly can. So what would happen if a true rogue planet, not a settled captured one, decided to take a shortcut through our inner solar system? The gravitational consequences would be catastrophic. As it plowed through, its immense pull would act like a wrecking ball on the delicate orbital clockwork of our solar system. The orbits of planets, from the gas giants to our own Earth, could be subtly or dramatically altered. A close enough pass could fling worlds into new, unpredictable paths, potentially hurling them into the Sun or out into interstellar space. It would be the ultimate celestial disruption, a reminder of the chaotic and dynamic nature of our galaxy, where dark, uninvited guests can wander into any stellar backyard. The loneliness of a rogue planet's journey may not be absolute. These dark worlds do not always travel alone. A planet ejected from its solar system can take its moons along for the ride. During the violent gravitational upheaval that flings a planet into the void, any large moons in stable orbit around it are likely to remain bound. Their primary gravitational allegiance is to the planet itself, not the distant star, so when the planet is cast out, its lunar family is pulled right along with it. This creates a miniature, self-contained system, a rogue planetary system drifting as a single unit through the galaxy. Think of it as a nomadic family, a planet and its moons forever bound together in their shared exile. This possibility transforms the image of a solitary wanderer into something far more complex and intriguing. A rogue planet could be the central body of its own tiny, dark cosmos, with one or more moons orbiting it in perpetual night. The implications for potential life within such a system are profound. While the planet itself might be a frozen wasteland, its moons could be worlds of surprising warmth. The key is tidal heating. If a moon orbits close enough to its giant planetary parent, the constant, uneven gravitational pull flexes and stretches the moon's interior. This friction generates immense heat, enough to melt ice and sustain vast global subsurface oceans of liquid water. We see this in our own solar system. Jupiter's moon, Europa, is frozen solid on the surface, but it is warmed from within by Jupiter's gravity, hiding a deep ocean that could potentially harbor life. Now transplant that entire dynamic into the interstellar void. A rogue gas giant with a large, icy moon would provide all the necessary ingredients. The planet's gravity acts as the engine, the moon's subsurface ocean becomes the habitat, and the deep space cold creates a protective, frozen shell. This moon would have no sun, no sunrise, and no concept of day or night. Its only source of energy would be the internal heat from its planetary partner and the chemical energy from its ocean depths. Entire ecosystems could evolve around hydrothermal vents on the ocean floor, completely isolated from the universe above, living in a warm, dark sea shielded by ice, while their parent world, a silent giant, hangs forever in a starless sky. This means a rogue planetary system could be a self-sufficient ark, carrying the potential for life across the galaxy, independent of any star. This lone wolf world has a name as poetic as its existence, a Steppenwolf planet. It is a rogue world that paradoxically carries all the ingredients for life within its frozen heart. The term describes a specific, hypothetical type of wanderer, one with just enough internal heat to maintain a thick, global ocean of liquid water sealed beneath a protective crust of ice. Imagine a planet that is not a solid ball of rock and ice, but a vast, dark aquatic world, its entire surface a frozen ceiling over a sunless sea. The warmth comes from within, a combination of radioactive decay in its core and perhaps the lingering heat of its violent birth. This internal furnace is faint, but in the absolute cold of interstellar space, it is just enough to create a stable, liquid sanctuary. The ice shield above is not a prison, but a blessing. It protects the inner ocean from the vacuum of space and the relentless cosmic cold, creating a sealed, self-contained environment that could remain stable for billions of years. What kind of life could possibly call such a place home? Without sunlight, photosynthesis is impossible. Life here would rely entirely on chemosynthesis, a process that draws energy from chemical reactions. On Earth, entire ecosystems thrive in the absolute darkness of the deep ocean floor, clustered around hydrothermal vents. These vents spew mineral-rich, superheated water into the cold depths, and the bacteria at the base of this food chain convert those chemicals into energy. In a Steppenwolf planet's ocean, similar vents on the seafloor would be the bustling metropolises of this dark world. The entire biosphere would be a deep-sea civilization, forever unaware of a sky or stars. Giant tube worms might sway in slow currents, blind shrimp-like creatures could scuttle across volcanic rock, and strange, translucent fish might drift through the perpetual night. There would be no day, no night, no seasons. The only constant would be the gentle warmth from below and the crushing pressure of the ocean and ice above. This lone wolf does not just wander, it carries a secret, a spark of life isolated and evolving in the infinite dark, a living world sailing through the galaxy entirely on its own. The silent expanse between stars holds more than just frozen gas giants. Our image of a rogue planet often defaults to a dark, Jupiter-like sphere, but the reality is far more diverse. Many of these interstellar orphans are likely terrestrial worlds, rocky bodies similar in composition to Earth or Mars. They are the ejected siblings of our own planet, cast out during the gravitational turmoil of their solar system's youth. When young planets jostle for position, it is not only the massive gas giants that get thrown from the nest. Smaller, rocky worlds can be just as easily flung into the void, becoming Earth-sized wanderers lost in the galactic dark. The fate of a rogue planet is shaped profoundly by its type. A gas giant with its immense size and thick insulating atmosphere is a master of heat retention. It cools slowly over billions of years, its interior remaining a reservoir of primordial warmth long after its ejection. This makes it a prime candidate for hosting warm, subsurface ocean moons, as its own gravitational pull can generate the tidal heating needed to sustain them. Yet for all its retained energy, a rogue gas giant offers no solid ground. Any potential for life would be confined entirely to its orbiting moons, as the planet itself is a swirling, storm-racked ball of gas with no surface to stand on. A rogue terrestrial planet presents a completely different set of possibilities and hardships. A rocky world, smaller and less insulated, would lose its internal heat much more rapidly. Its surface would freeze into an airless, globally glaciated crust of unimaginable cold. Without a thick atmosphere to trap what little warmth remains, the surface becomes a permanent, sterile wasteland. Yet life, if it ever existed, might simply retreat. Deep beneath that frozen shell, in the rocky mantle heated by radioactive decay, pockets of liquid water could persist for eons. A subsurface ocean, warmed by the planet's own geothermal heart, could become a sealed refuge. This environment would be more isolated than any on Earth, a sunless aquifer hidden beneath miles of rock and ice, but it is a habitat that could theoretically endure. So while a rogue gas giant might be a warm engine for its moons, a rogue terrestrial world could be a frozen safe for its own hidden interior sea. The galaxy's loneliest worlds come in many forms, each carrying its own unique story of survival in the endless night. This blurry line in cosmic classification forces us to ask a fundamental question. What truly separates a planet from a star? The answer often lies in a single, violent act that never happens. A brown dwarf is often called a failed star. It forms just like a star from the collapse of a cloud of gas and dust, but it simply does not have enough mass to ignite sustained nuclear fusion in its core. It is an object caught in a cosmic gray area, too big to be a planet but too small to be a true star. So where do we draw the line between a very large rogue planet and a very small brown dwarf? Astronomers often use a specific, fiery threshold known as the deuterium burning limit. Deuterium is a heavy form of hydrogen. If an object has about 13 times the mass of Jupiter or more, the pressure and heat in its core becomes so intense that it can briefly fuse this deuterium. This is not the long-term hydrogen fusion that powers stars like our Sun, but a shorter, fainter blaze. This deuterium burning limit, around 13 Jupiter masses, is a commonly used, though debated, boundary. An object above this mass is typically classified as a brown dwarf, while an object below it is considered a planet. But what if a rogue planet formed alone from a collapsing cloud, just like a brown dwarf, but it only had 10 Jupiter masses? It would be below the deuterium limit, so we would call it a planet, even though its birth story is stellar. This is why the formation history is so crucial and why the debate remains so vibrant. Imagine two objects adrift in the same patch of interstellar space. One is a rogue gas giant, a colossal world with 12 times the mass of Jupiter. It is a deep, banded sphere of swirling, cold gases, its internal heat a faint remnant from its formation. Next to it drifts a small brown dwarf with 15 Jupiter masses. It might appear similar in size, but for a brief period in its cosmic infancy, its core was a furnace burning deuterium. That faint historical fire is the technicality that places them in different categories. This distinction is more than just academic labeling. It shapes the object's entire evolution, its internal chemistry, and its long-term fate. The search for rogue planets constantly brushes against this frontier, reminding us that nature does not always fit into our neat little boxes. Freedom comes with tremendous velocity. The same violent ejection that hurls a planet into the void also grants it an incredible speed, a slingshot effect that can send it hurtling through the galaxy at dozens of kilometers every single second. To put that into perspective, our own solar system orbits the galactic center at about 220 kilometers per second, but we are all moving together. A rogue planet is a solo sprinter, its velocity measured relative to the silent background of the galaxy itself. This means its journey across the immense gulf between stars is not an impossibly long one. While stars are separated by light years of emptiness, a rogue planet moving at such a pace could cross from one spiral arm of the Milky Way to another in a span of mere millions of years. That may sound like a long time, but on the cosmic calendar, it is a relatively quick trip. Our Sun takes about 230 million years to complete just one orbit around the galaxy. A fast-moving rogue planet could accomplish an interstellar crossing in a fraction of that time. This turns them into potential cosmic couriers. A world ejected from a dying star system could, within a few million years, carry the raw materials for life, or even life itself locked in a subsurface ocean across vast interstellar distances. They are not just drifting, they are racing through the darkness on voyages that reshape our understanding of how matter, and perhaps even biology, could travel between the stars. The silent, cold nature of rogue planets makes them nearly invisible, but a new eye in the sky is designed to see their faint glow. The James Webb Space Telescope is revolutionizing our search for these dark wanderers. Its entire design is tailored for this exact purpose, equipped with incredibly sensitive infrared instruments that can detect the subtlest whispers of heat in the cosmic cold. While previous telescopes gave us glimpses, Webb can perform a kind of cosmic chemistry on nearby rogue planets. It uses a technique called spectroscopy, where it captures the light from an object and splits it into a rainbow of colors, a spectrum. Specific molecules in a planet's atmosphere leave unique fingerprints on this spectrum, dark lines that reveal their chemical identity. For the first time ever, we could point a telescope at a solitary, starless world and ask what its air is made of. The potential discoveries are staggering. If Webb detects molecules like methane or ammonia in a rogue planet's atmosphere, it could be a powerful indicator of active geothermal processes deep within the world. These gases are often replenished by volcanic activity or hydrothermal vents, suggesting a warm, geologically active interior. And where there is persistent heat and chemistry, the possibility for life emerges. The ultimate, breathtaking goal would be to detect a biosignature, a molecule that is almost exclusively produced by living processes. On Earth, the abundant oxygen in our atmosphere is a classic example, a gas that would quickly vanish without life constantly replenishing it. Finding a similar imbalance in the atmosphere of a rogue planet would be a discovery of monumental proportions. It would mean that life can not only survive but potentially thrive in the absolute darkness of interstellar space, sustained entirely by the internal heart of a world. Webb turns these cosmic phantoms into real, tangible worlds we can begin to analyze, bringing us closer than ever to answering the profound question of whether we are truly alone in the universe. This dark ark concept leads to one of the most profound ideas in astrobiology, the theory of panspermia. Imagine a rogue planet not just as a potential habitat, but as a life-bearing vessel on an interstellar voyage. If a world with a subsurface ocean full of microbial life were ejected from its system, it could theoretically carry that life across the galaxy, preserving it for eons within its protective icy shell. This wandering world becomes a Noah's Ark on a cosmic scale, a self-contained biosphere sailing through the void. The concept of panspermia suggests life could be spread between stars, not by design but by celestial chance. A rogue planet is the ultimate vehicle for this process. It offers stability and longevity that a small asteroid or comet simply cannot provide. An asteroid might be sterilized by radiation or lack the resources to sustain life for long periods. But a large rogue planet with a deep ocean is a different story. Its liquid interior, warmed from within and shielded by miles of ice, could maintain a stable environment for billions of years, far longer than the lifespan of most stars. This is a sanctuary that could outlast entire cosmic eras. The odds of such an ark ever delivering its cargo to a new world seem astronomically low. The distances between star systems are immense, and the chance of a random rogue planet passing close enough to another planetary system to transfer material is incredibly slim. But here is where the vastness of time comes into play. The universe is nearly 14 billion years old. Over these cosmic timescales, with trillions of potential arcs drifting through the galaxy, even the most improbable events might not just be possible but inevitable. A close gravitational encounter could nudge a rogue planet into a new system, or it could pass through a system and have its moons or even pieces of its icy crust captured by a planet like Jupiter or Saturn. The microbes frozen in that ice, dormant but alive, could then find themselves in a new ocean on a moon like Europa, seeding life in a new stellar neighborhood. This transforms our view of life in the universe from something that arises in isolated ponds to a potential galactic phenomenon, where life, once it begins, might be carried on the tides of darkness between the stars. Their silent presence could one day transform the galaxy into a traversable archipelago. The sheer number of rogue planets offers a radical solution to the greatest challenge of interstellar travel, the immense, empty distances between stars. A generation ship on a millennia-long journey would face a terrifying void, but what if that void was not entirely empty? These dark worlds could act as cosmic stepping stones, providing vital resources in the deep abyss. The most crucial resource they offer is water. Many rogue planets, especially those that formed in the outer regions of a solar system, are likely composed largely of water ice. To a passing starship, this ice is a treasure trove. It can be mined and split into hydrogen and oxygen, the fundamental components of rocket fuel. It can also be purified for drinking water and used to grow food in onboard hydroponic bays. A rogue planet would not just be a rock in the distance. It would be a refueling depot and a resupply station, a place to harvest the very elements needed to sustain both the ship and its crew for the next leg of their epic voyage. This turns a seemingly endless journey into a series of shorter, more manageable hops between known waypoints. The psychological impact would be just as profound. For a crew born and raised aboard a ship, the approach to a rogue planet would be a monumental event. After years of staring into the featureless black, a tangible world would grow in their viewports, a destination. They could send probes to map its frozen surface and drill into its icy crust, a mission providing purpose and a connection to a real, physical world, however dark and cold. While this remains a vision for the far future, it grounds the study of these objects in a tangible, human aspiration. Cataloging rogue planets is not just an academic exercise. It is the first step in drawing a map for our descendants, a chart of the hidden oases in the galactic desert. Spotting one of these dark travelers directly is a challenge that pushes our technology to its absolute limit. The fundamental problem is simple yet profound. A rogue planet produces virtually no visible light of its own. It is a cold, dark object adrift in an even colder, darker void. Without a nearby star to act as a spotlight, there is nothing to illuminate its surface for our telescopes to see. What little energy it does emit is in the form of infrared radiation, the faint heat signature left over from its formation. This glow is incredibly weak, a whisper of warmth against the overwhelming cold of space. Trying to see it is like trying to spot a single, cooling ember from a campfire that was extinguished long ago, lost in the immense darkness of a continent-sized forest. This is why microlensing has been our primary window into this hidden population. It cleverly bypasses the need to see the planet itself, instead detecting its gravitational shadow as it drifts in front of a distant star. Microlensing gives us powerful statistics confirming these worlds exist in staggering numbers, but it turns them into abstract data points, fleeting flashes in a sea of stars. We know they are there, but they remain phantoms, concepts rather than concrete worlds we can study in detail. The next great leap requires us to see them for ourselves, to pull them out of the statistical shadows and into the light. This is the ambitious goal of a new generation of observatories. The upcoming Nancy Grace Roman Space Telescope, equipped with a powerful infrared eye and a colossal field of view, is designed to do exactly that. It will not rely on chance alignments alone. By staring deeply at vast star fields for long periods, it could directly image the closest and largest rogue planets by capturing their faint infrared glow. This would be a monumental shift. Instead of inferring a planet's existence from a temporary brightening of a star, we would see the planet itself as a distinct, solitary pixel of light. We could measure its temperature, estimate its size, and begin to understand its composition. The Roman telescope could transform these cosmic phantoms from statistical ghosts into tangible worlds, the first direct portraits of planets living in eternal night. Even in the deepest dark, a rogue planet might hold onto its sky. While most worlds adrift would freeze solid, larger ones, especially gas giants, have the gravity to maintain a thick global atmosphere for billions of years. This is a crucial difference from our solar system, where a star's constant solar wind steadily strips away at planetary atmospheres over time. But a rogue planet experiences no such stellar bombardment. Its atmosphere is shielded from that relentless gale, left to settle into a state of profound and permanent calm. It becomes a sealed envelope of gas, a relic of the planet's birth, preserved in the perfect vacuum of interstellar space. This stable shroud creates a world that is perpetually clouded, its surface, if it has one, hidden beneath layers of swirling, frozen gases forever untouched by starlight. But the truly revolutionary idea applies to rocky wanderers. A terrestrial rogue planet, an Earth-sized world cast adrift, would not necessarily be a bare, frozen rock. If it managed to hold onto a very specific kind of atmosphere, something unexpected could happen. Imagine a thick blanket of hydrogen gas, the lightest and most common element in the universe, enveloping the planet. Hydrogen is a remarkably effective greenhouse gas. On such a world, the faint internal heat seeping up from the radioactive core would not simply radiate out into space. Instead, this hydrogen atmosphere would act like an insulating coat, trapping that geothermal warmth at the surface. This is the concept of a hydrogen greenhouse world. The planet's own internal heart, however faint, becomes the furnace, and the atmosphere becomes the glass of a planetary greenhouse, concentrating the heat. The result could be surface temperatures rising to levels we would consider habitable, all without a single ray of sunshine. A world like this would be shrouded in a perpetual global fog, its surface bathed in a dim, ambient warmth generated from within. The sky would not be black, but an opaque, glowing murk lit by the planet's own trapped energy. Could liquid water exist on the surface under such a dense hydrogen sky? It is a tantalizing possibility, one that turns the image of a frozen terrestrial rogue completely on its head. Instead of a block of ice, it could be a dark, steamy world, its oceans kept liquid not by a sun, but by the planet's own sealed atmospheric prison. This uncertainty is the great paradox of rogue planets. We know they are staggeringly common, yet we know almost nothing about them as individuals. Microlensing surveys have given us a powerful but blurry snapshot. A census that confirms a vast population exists but cannot tell us what these worlds are actually like. The estimates themselves vary wildly. Some studies suggest there could be 2 rogue planets for every star in the galaxy. Others propose a number so high it reaches into the trillions. This discrepancy arises because we have only sampled a tiny, narrow slice of the Milky Way, like trying to guess the entire population of Earth by counting the people on a single city block. Our data is heavily biased toward a specific type of rogue planet, those within a certain mass and distance range that are perfectly positioned to cause a microlensing event. We are effectively seeing only the very largest and most conveniently located wanderers. What about the smaller, Earth-sized rogue planets? Their gravitational lensing effect is so minuscule that our current technology can barely detect it. They are the silent majority within the silent majority, countless terrestrial worlds drifting unseen. Their composition is another profound mystery. Are they mostly icy giants, frozen remnants of outer solar systems? Or are they rocky, metallic worlds, the ejected cores of what might have been Earth-like planets? We simply do not know. This vast ocean of ignorance is precisely what makes this field so electrifying for astronomers. Every unanswered question is a beacon for future research. Determining the true mass distribution of these worlds will tell us if planetary ejections favor gas giants or if smaller, rocky planets are just as commonly thrown into the dark. Uncovering their composition will reveal if our own solar system is typical or a bizarre outlier in its architecture. This is not a settled science. It is a wide open frontier, a gravitational wilderness we are only just beginning to map. Their profound isolation makes them perfectly preserved relics of the cosmic past. A rogue planet is a time capsule sealed in the deep freeze of interstellar space for billions of years. Unlike planets bound to stars, which are constantly weathered and altered by stellar winds, radiation, and gravitational interactions, these wanderers exist in a state of suspended animation. Their surfaces and atmospheres are not subject to the constant erosion that reshapes worlds like Earth or Mars. They are pristine vaults, locking in the original chemical and physical conditions from the moment they were born or cast out. This pristine preservation offers a window back to the galaxy's youth, a direct sample of the materials and processes that built planetary systems when the universe was far younger. Planets within active solar systems have their histories constantly rewritten. Our own Earth's surface is a dynamic palimpsest where plate tectonics, volcanic activity, and erosion have erased almost all evidence of its earliest years. Even the gas giants, like Jupiter, have had their atmospheres stirred and altered by billions of years of internal heat and external influences. A rogue planet, however, has been sitting in a perfect dark vault. Its atmosphere, if it has one, remains the same primordial mix of gases it started with, untainted by photochemistry from a parent star. Its frozen surface, whether of rock or ice, could contain isotopic ratios and chemical signatures long since lost on more active worlds. Studying one of these dark wanderers would be like opening a geological time capsule from the dawn of planetary formation. It would allow us to test our models of how solar systems are born with direct, uncontaminated evidence. We could finally know the true initial composition of a planet, answering fundamental questions about the distribution of water, organic molecules, and heavy elements in the protoplanetary disks that swirled around infant stars. This is information that is simply unavailable anywhere else, a frozen record of the galaxy's early days, waiting in the darkness to be read. This cosmic census of invisible worlds leads us to one of the greatest puzzles in all of science. The matter we can see, the stars and galaxies and planets, accounts for only a tiny fraction of the universe's total mass. The rest is something we cannot see or directly detect, a mysterious substance we call dark matter. Its gravitational pull is the only way we know it is there, sculpting the shapes of galaxies and holding them together. For a time, scientists wondered if rogue planets could be the answer. Could this missing mass be made of countless trillions of these dark, planet-sized objects drifting in the vast halos around galaxies? These hypothetical objects were given a name, MACHOS, which stands for Massive Astrophysical Compact Halo Object. The idea was compelling. It would mean the universe's biggest mystery was solved by a sea of its most common, yet unseen, planets. Astronomers hunted for these MACHOS using the same gravitational microlensing technique we use to find rogue planets today. They watched millions of stars in nearby galaxies, waiting for the telltale brightening that would signal an invisible, planet-sized object drifting through the dark halo of our own galaxy. They found some. The surveys did confirm the existence of a population of these compact objects, likely a mix of rogue planets and faint, ancient stars. But the numbers were far too small. There were not nearly enough MACHOS to account for the immense gravitational grip of dark matter. The vast majority of the universe's mass is still something else, something far more exotic and elusive than planets. So while rogue planets are not the dominant form of dark matter, this investigation profoundly shaped our understanding. It showed how the search for one mystery can illuminate another. The hunt for MSCHOS helped pioneer the microlensing techniques that later proved the existence of a vast sea of rogue planets. It also set a crucial limit, telling us that whatever dark matter is, it is not simply a universe filled with dark, frozen worlds. This speculative chapter reminds us that these solitary wanderers are more than just planetary curiosities. They are pieces of a larger cosmic puzzle, their gravity subtly influencing the structure of the galaxy itself, even if they are not the final answer we seek. Their journey is measured not in millions but in trillions of years. The ultimate destiny for most rogue planets is a slow, silent fade into the cosmic background. They will continue their solitary drift through the galactic arms, their internal heat source gradually diminishing as radioactive elements decay. This is a cooling process of unimaginable slowness, a descent into an even deeper cold that will eventually leave them as nearly inert, frozen spheres, little more than the faintest whispers of warmth in the void. Yet this serene fate is not guaranteed for all. The galaxy is a dynamic place, and chance encounters can rewrite a wanderer's story. A rogue planet passing relatively close to a star system could be snared by the star's gravity, pulled from its aimless path and forced into a new, permanent orbit. It would become an adopted world, a planetary immigrant in a foreign solar system, its lonely journey ended by a new stellar master. This capture would likely place it in a distant, wide orbit, a perpetual outsider in an established family of planets. More dramatic endings are also written in the stars. A direct collision with another rogue planet, or perhaps a dense asteroid, would be a catastrophic event of pure chance, shattering both bodies into fragments. The most violent finale awaits any wanderer that strays too close to a black hole. The immense, uneven gravitational pull, the tidal forces, would stretch the planet into a long, thin stream of superheated matter before it was completely consumed. This spectrum of fates, from the quiet fade to the explosive end, underscores the nature of the galaxy itself. It is not a static museum, but a living arena of constant gravitational interaction, where the paths of dark, solitary worlds are forever subject to the pull of unseen forces. This relentless discovery of solitary worlds directly confronts one of astronomy's most fundamental questions. What exactly do we mean by the word planet? Our current official definition, established by the International Astronomical Union, is surprisingly local. It states that a planet must orbit the Sun, must be large enough to be rounded by its own gravity, and must have cleared its orbital neighborhood of other debris. That first requirement creates an immediate and glaring problem. It is entirely Sun-centric. By this strict definition, not a single planet outside our solar system technically qualifies, and every rogue planet in the galaxy is instantly disqualified. It is a rule book written for our own celestial backyard, completely ignoring the vast cosmic city that lies beyond our fence. This has sparked a vibrant and necessary debate among scientists. The goal is to forge a new, universal definition, one that can describe a planet based on its intrinsic physical properties, not its address. The core idea is to focus on what a world is, rather than where it happens to be. Many astronomers argue the most crucial characteristic is that formative process. If an object forms from the disk of material around a star and has enough mass to become spherical, it is a planet, regardless of whether it stays in that system or is later ejected into the void. This would reclassify ejected worlds as a type of planet, acknowledging their shared origin story with our own Earth and Jupiter. But this approach runs headlong into the puzzle of those solitary objects that formed alone in deep space. If a ball of gas coalesces directly from an isolated interstellar cloud, never having orbited a star, is it a planet or a very small brown dwarf? The line remains blurry, and any new definition must find a way to draw it. This is not just academic semantics, it is a struggle to keep our language in step with our knowledge. Every time we find a new class of object that does not fit our old boxes, we are forced to rethink our categories. From reclassifying Pluto to grappling with rogue planets, these debates are a sign of a healthy, evolving science. They prove that our understanding of the cosmos is not set in stone, but is a living, breathing narrative constantly rewritten by the darkness itself. Science fiction has long embraced the dark allure of these solitary worlds, transforming them into canvases for our deepest fears and wildest speculations. In the expansive universe of Alastair Reynolds, rogue planets become the ultimate refuges for isolated human colonies, outposts clinging to survival by harnessing geothermal energy within a sunless void. These stories explore the profound psychological toll of such existence, where generations live and die beneath an ice shell, their entire universe defined by the hum of machinery and the crushing pressure of the eternal dark above. A far more visceral terror awaits in the classic Star Trek episode, where a so-called planet of death exhibits bizarre properties that drive visitors to madness and violence. This portrayal taps into the primal fear of the unknown, where the planet itself is a malevolent entity. These fictional worlds are frequently stages for cosmic horror, serving as hidden bases for ancient alien civilizations or laboratories for experiments that warp the very fabric of time. The common thread weaving through these tales is the theme of absolute isolation. A rogue planet is the perfect setting for a story about the last survivors of a species, a secret too dangerous for the galactic core, or a phenomenon that defies all known laws of physics. They are the ultimate blank slates, distant and enigmatic enough to hold any mystery an author can conceive. This creative fascination mirrors our own innate curiosity about the darkness between the stars, giving shape to the formless dread and wonder that these real, drifting worlds inspire. Some of the most revealing rogue planets are not ancient drifters but cosmic newborns. Astronomers have spotted free-floating planetary mass objects still within the stellar nurseries where they were born, like the Orion Nebula. These are infants on an astronomical scale, sometimes just a few million years old. Their youth is their most revealing feature. Freshly formed, they are still hot and bright from the gravitational energy of their own collapse, glowing intensely in the infrared. This makes them far easier to detect and study than their cold, ancient cousins that have been drifting for billions of years. Their presence in these active star-forming regions presents a fascinating puzzle about their origin. Were these worlds born in protoplanetary disks around young stars and then violently ejected almost immediately after their formation, a planetary ejection on a hyper-fast track? Or did they condense directly from isolated clouds of gas and dust, much like stars do, never knowing the gravitational pull of a parent star? Their location provides a critical clue. Finding them deep within the turbulent gas clouds of a nebula suggests the latter is a real possibility, that some planets can simply form alone from the start. These young wanderers offer a pristine laboratory. By studying their atmospheres and temperatures, we can glimpse the conditions of a planet's earliest moments, a snapshot of planetary infancy frozen in time. They hold the answers to fundamental questions about how planetary mass objects come into existence, whether around a star or in the profound solitude of deep space. This research is actively rewriting the first chapter of a planet's life story. Even in the deepest isolation, a rogue planet might generate its own light. A terrestrial world, one with a molten, metallic core churned by internal heat, could maintain a powerful magnetic field. Just like Earth's geodynamo, the convection of that liquid metal would create a planetary magnetosphere, an invisible shield extending far into space. This magnetic field would interact with the sparse but ever-present charged particles of the interstellar medium. Without a star to bombard it with a solar wind, the source is different but the physics remains the same. As these free-floating cosmic rays and ions are captured by the planet's magnetic poles, they would slam into the thin, frozen remnants of its atmosphere. The result would be a permanent, silent aurora. Imagine standing on the frozen surface of this world. the sky is not pitch black, but instead a colossal, shimmering curtain of green and violet light dances from horizon to horizon. There is no sun to make it set, no dawn to extinguish it. This breathtaking light show is constant, a brilliant spectacle illuminating the glaciers and canyons of a world that has never known daylight. It is a beautiful and profoundly lonely phenomenon, a planet painting its own skies with color for an audience of none, a testament to the hidden dynamism that can persist in the eternal night. The closest known rogue planet drifts through space a mere light years away from Earth. Scientists have identified several candidates, like the intriguing CFBDS IR 2149-0403, a world with about 4 to 7 times the mass of Jupiter, located just 100 light-years from our solar system. While that may sound distant on the galactic scale, it is practically our next-door neighbor. Yet the truly staggering possibility is that an even closer wanderer remains undetected, perhaps even closer than the nearest star, Proxima Centauri. Given the sheer abundance of these dark worlds, it is statistically likely that one is lurking in the immediate darkness surrounding our solar system. Finding such a nearby rogue planet would be the astronomical discovery of a generation. Its proximity would transform it from a faint, statistical blip into a tangible world we could study in stunning detail. Our most powerful telescopes, like the James Webb, would be able to directly image it, analyzing its atmosphere for signs of methane, water vapor, or even more complex organic molecules. We could measure its temperature, map its cloud patterns if it is a gas giant, and determine its rotation rate. This would not be a fleeting microlensing event, but a permanent new member of our local celestial landscape, a dark companion we could observe for centuries. The data gathered would answer fundamental questions about the composition and formation of these solitary worlds, providing a pristine sample of a planetary object untouched by a star's influence. The hunt for this closest wanderer is a quiet race, with astronomers meticulously scanning the darkest patches of our local interstellar space, knowing that at any moment one of these cosmic orphans could reveal itself, hiding in plain sight just beyond the planets we know. This profound silence from the cosmos might have a simple, chilling explanation. We have been searching for life in all the wrong places. The Fermi paradox famously asks, if the universe is so vast and old, where is everybody? Why have we not found any signs of intelligent civilizations? One compelling answer is that they are not on planets orbiting stars, basking in the light where we would expect to find them. They are out in the dark. A technological species that evolved on a rogue planet would be virtually undetectable to our current methods. Think about how we hunt for aliens. We listen for radio transmissions leaking into space, but a civilization on a sunless world would have no need for powerful long-range communication. Their signals would be faint, directed inward, and swallowed by the immense distances of interstellar space. We look for the telltale dip in starlight as a planet transits its sun, but a rogue planet has no sun to transit. It is a ghost leaving no shadow. We search for artificial lights on the night side of worlds, but on a rogue planet, every side is the night side, and any lights would be dim, powered by geothermal energy, and lost in the glow of the galaxy. Their entire world would be cloaked in a perfect natural stealth system. If the galaxy is filled with billions of these dark arks, then intelligent life could be incredibly common, yet forever isolated. Each civilization would be an island universe, unaware of the others, thriving in its warm, subsurface ocean or beneath a dense, insulating atmosphere. They might gaze up at their own icy ceiling or a shimmering aurora, with no concept of stars, never knowing that the pinpricks of light in the theoretical sky are other suns, other possibilities. The great silence is not a sign of our loneliness, but a testament to life's ingenuity in hiding in the most unexpected of sanctuaries, the cold, dark, and silent hearts of orphaned worlds. The final frontier in this search lies with missions designed to hunt the darkness itself. The Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct a galactic bulge survey on a scale never before attempted. By continuously monitoring hundreds of millions of stars toward the crowded center of our galaxy, it is expected to catch thousands of these fleeting microlensing events, transforming rogue planets from statistical anomalies into a well-defined population. Roman will not just find more of them, it will find different kinds, revealing the true diversity of these dark worlds, from Jupiter-sized giants to potentially Earth-mass wanderers we can barely detect today. This survey will paint the first comprehensive map of this hidden archipelago. Beyond mapping, our ambitions stretch to visitation. Concepts for interstellar probes, like those considered by initiatives such as Breakthrough Starshot, envision tiny, laser-propelled craft flying at a fraction of light speed. While their primary target might be a star system, a nearby rogue planet would be an equally compelling destination. Imagine a tiny spacecraft decades after its launch, entering the silent space around a solitary world. It would beam back the first ever close-up images, revealing a frozen surface of ancient ice and rock, untouched for billions of years. We could analyze its atmosphere directly, drill into its crust, and lower sensors into the fissures of its icy shell, searching for the warmth of a subsurface ocean. This would be humanity's first tangible encounter with a planet completely independent of any star, a profound moment that would forever change our understanding of what a world can be. These future missions promise to pull these cosmic phantoms into the light, turning the greatest mystery of the interstellar dark into a new field of exploration. So we arrive at the end of our journey, a voyage that has taken us from violent stellar ejections to the possibility of life in sunless seas. The truth we have uncovered is staggering. Rogue planets are not rare anomalies. They are the silent majority, outnumbering the stars themselves. They challenge our very definition of a world and shatter the notion that life requires a sun. Each one is a profound mystery, a frozen time capsule from the dawn of planetary formation, and a potential ark sailing the galactic currents. This field of astronomy is in its infancy, a frontier wide open for discovery. Every new observation promises to reshape our understanding of what a planet can be, where life might thrive, and our own place in a cosmos that is far darker and far more populous than we ever dreamed. The next time you look up at the night sky, remember that the true story of our galaxy is not written only in the points of light you can see. It is held in the countless dark, silent worlds adrift between them, each carrying an untold story through the endless night. What do you think the greatest secret of these cosmic orphans will be? Share your thoughts and questions in the comments below, and subscribe for more deep dives into the mysteries of space.